Good evening, Professor. I'm here to present my topic 5. As we scroll all the way to the top, it's about statistical modeling. Objective 1, we were asked to determine if there's a significant difference in mean weight between males and females. I downloaded a cardiovascular disease health data set. And here you can see kind of a summary of it. If we want to look at the count, there's well over 500 here. There's 70,000. So plenty of people here to look at. So carrying on, as we can see, based on the t-stat and the p-value, there is a significant difference in the mean weight between males and females. This did not occur by chance. This is intentional biology, right? And here's my report on that. So on task number 2, we were asked to calculate and interpret the correlation coefficient between the height and weight. And as we can see right here, the analysis yielded a correlation coefficient of 0.29, indicating, and just by looking at the graph, we can see there's a positive relationship, but it's just really weak. It's not very dramatic. So on task 3, we were asked to build a linear regression model to predict weight based on height. So here we can see the mean squared error of 192.85 and the R squared of 0.09. And that just kind of tells us that there's something else going on here that's not just height that makes the weight higher or lower, right? So it does not strongly explain the variance. I said that so much better down here. There's our residuals. Here's my report. So then number 4, objective was to predict weight based on height using a multiple regression model. I found this OLS regression results like the summary. I don't know if I've ever used it before, but I love it. It's amazing. So carrying on, here we have our VIF and our residuals. So the insights that we can really gather that the coefficients for height and weight were positive, suggesting an increase in these variables. So an increase in height and an increase in age does have an increase in weight. But only about 9% weight variability is explained by height and age. So not a whole lot there. So looking at the VIF calculated for multicollinearity, the values are below 10, so there's not really any concern there. And then there's no significant pattern in the residuals, suggesting that there's a lot of heteroscedasticity. So then we were asked to kind of do it again, and I picked a different data set because in the task it said that we could. So I picked a Pokemon data set. There are lots and lots and lots and lots of Pokemon in here. So we were asked to discuss common assumptions of linear regression models and demonstrated violation. So here I was looking at the assumptions. Okay, so the assumptions are linearity. The relationship between independent and dependent variables should be linear, right? Heteroscedasticity, the variance of error terms or the residuals is constant across all levels of independent variables. Violations of this assumption can be detected through residual plots. So these are the 2 assumptions that we're looking at. So if we look down here, I did a Bartlett test on this one. So here's my Bartlett test statistic and my p-value. So as we can see, indicated by the Bartlett test and the p-value, it suggests the model's violation of homoscedasticity assumption. And this issue can lead to inefficient estimates and unreliable testing. Sorry, I ran out of time, so I'm just going to get through this really quickly. I was on the last one. So comparing the nonlinear regression model comparing the linear regression to the nonlinear regression model, we can definitely see just by looking at the graphs that this one works a lot better for our data set. It's a lot tighter. The mean squared error, the MSE and the R squared are much higher, much more conducive to this particular data set, dealing with nonlinear relationships. So this polynomial regression model is definitely more effective in the Pokemon stats and probably the other data set as well. Anyway, so here are my sources down below. Have a great evening.